In this video, we're going to work through the asynchronous counters activity for digital electronics. We're going to start by reviewing some of the fundamental components and concepts I've been working with in this unit, specifically flip-flops and counters. We're going to talk a little bit about the design elements and decisions to build those flip-flops into functional sequential logic circuits. And specifically, we're going to build a 4-bit modulus 10 counter, which is one of the components that goes into the 60-second timer build. So this is an example of the design we're going to be implementing. However, this is a multi-sim screenshot, and so we are going to use this as our overall guiding document, but we're going to have to make some design decisions here, some decisions about how to implement this, because specifically we do not have access to a 4-input NAND gate here, the 74LS20 in Circuits Cloud. We also don't have the exact component of a 74LS93, which is just the MSI level, the medium scale integration for a 4-bit counter. We do have a 4-bit counter, but we won't need to worry about multiple inputs here. We'll have just a clock signal coming in to control our writes, and our reset button is going to be simplified to the control structure here that we implement on our own. And we'll get back to this design and talk about it more, but this is a good approximation of all the things we're talking about and what we're going to actually build. So again, to review, I want to talk about flip-flops a little bit. This is where we started, Unit 3. Remember that flip-flops are a fundamental component to save state. Another way to say that is they are our first element of storage, something that we can use to save a single bit of information per flip-flop. And that's very important for the transition from combinatorial logic, which is what we did primarily in the first part of the class, which is an instantaneous output based on what our logic is. What happens when we turn the power on to our circuit? We saw the light or not light immediately. We want to get to the point where how can we take units of information and combine them in meaningful ways to create intended behavior. So again, flip-flop is a pretty fundamental component transitioning into sequential logic. And we're going to look at two main versions, the D flip-flop and the JK flip-flop. I'll also talk a little bit about a D latcher. And then really we're going to look at counters, which is an application of flip-flops, one of the most standard ones. And again, what we're doing here is we are trying to build this ability to save and manipulate information into a meaningful circuit for some specific purpose. And I want to look a little bit about what flip-flops actually do and then how to use those possibilities. And we're going to focus on the asynchronous inputs for our flip-flops, which preset and clear. Again, asynchronous meaning we can override what's already in and stored there. And then really what we're doing is we're building an asynchronous counter, and we're going to use modulus is the idea that we want to limit the range of our count for some specific reason. In our case, we want our counter to go, or to appear to go, from 0 to 9 instead of just counting all the way through 4 bits or a single hexadecimal unit, right? We don't want to go from 0 to F. We want to go from 0 to 9 because that'll be our seconds, our singular seconds place for our overall build. And again, what we're really working up to is we're going to actually build a circuit on our new circuit design software, Circuits Cloud. So this is the base slide for what is a D flip-flop. And a D flip-flop is the starting place for storing this information. And what we want to know is exactly how this works. And so D here is our input. And this means that we have a signal which is coming into this flip-flop. And then what we're actually doing here is we're going to take that signal in, that D, and on the rising edge, right, when we go from 0 to 1 on our clock signal, right, that rising edge, we're going to take the value on D that's currently there, and we're going to store it to the flip-flop. And anything that we have stored here, right? Remember, we can only store a single bit. So this is either going to be a 0 or a 1 on that rising edge. It writes it. And then we'll be able to see that, or really that signal will be output on Q, which is our output for a flip-flop, which is just showing us what the current save state is of that flip-flop. And then complement Q, or not Q, is just the opposite, the binary opposite of whatever's being stored. So we see here in the output, right? If Q is our output, if we've saved as 0, right, then not Q is simply going to be 1, the opposite. And again, this is specifically for rising edge. And then we also have the other main variation of flip-flop that we work with in this class, which is the JK flip-flop. And this is a very similar idea where we have this component which is going to save a single bit of information based on the inputs. The main difference between D and JK flip-flop, as you notice here, is we have a couple more options. Because we have not one but two control or input signals, all right, that means that we can actually think about having 4 total different possibilities in how we deal with this information. And so we see here in our actual output, our save state in this Q column, all right, is it's not just 0 and 1 like we had where it's saving whatever the input is. We have the possibility to not change any information, right? So this means whatever is saved there, just have that be the output. That's like the normal one, right? And then we also have toggle, which is helpful in certain ways because we're taking the opposite of what's saved. Right, so remember that complement Q or not Q is simply going to be representing whatever the opposite of what we have stored is here. So we can toggle or flip that bit if both J and K are high. And again, this is all rising edge, but the asynchronous comes from these two possibilities right here, which will be built into our other flip-flops. But again, clear and preset are this idea that we are overriding whatever information was stored, so we don't care what was stored here and what is. We are, for whatever reason, clearing out this information at 0, which is what we'll actually be doing in our counters, right? To simulate having a range. So instead of having a 4-bit counter go from 0 to F, if we want it to look like it's a decimal number, base 10, then we say, just kidding, when you get to 10 or 1010, go ahead and hit that clear button and 0 everything out, regardless of whether you're about to go to 11 or whatever. And then set is the same thing, but the other side, where we're preset is usually what it's called, setting to 1. So this is rising edge. This is just to show you the distinction between a positive edge trigger and negative edge trigger. Again, it's usually called rising edge or falling edge. And notice these are the exact same outputs. The only difference is that these are actually only going to be written, the values that we're saving are only written on the falling edge of the clock when the clock signal goes from high to low or from 1 to 0. And the main distinction, and the reason I included this, is notice in the multi-sim screenshot of this flip-flop, the only distinguishing factor that this is a negative edge trigger flip-flop is this inverter gate right here, right in front of the clock signal. Remember when we looked at the NOT gate originally, it looks like an arrow and a circle. Well, that arrow is actually a relay, right? The circle is the inverter or NOT gate. So this is how you distinguish positive and negative edge trigger flip-flops, just based off of the circuit design, circuit picture. There's also a distinction of a flip-flop versus a latch. Latch, sometimes called a D-latch or transparent latch, is similar to a flip-flop in that it saves state, but the main distinction is that a latch is going to show whatever the input is to the latch, right? So the way we might distinguish this is we'd say that flip-flops are edge sensitive, meaning that the information is only saved on either the rising or the falling edge, however it's set up, right? But only saved on a rising or falling edge of the clock signal. Whereas in a latch, the enable is just going to be taking into account whatever the level of the input is. So if, the input is 1 and on, then, it's saving 1 and it's saving on. So that's edge sensitive versus level sensitive. And that's, flip-flop versus D-latch or transparent latch. All right, so this is a first design of how do we actually use this behavior in a meaningful way. And so this is an example of a 2-bit counter. And this is specifically something we want to look at for working into our build, because we notice here, we notice a couple of things. First, I want to point out the clock signal. All right, this is going to be the same for our build, except that our build is going to be 4 bits instead of 2. So this is one of the more difficult things to realize here, is that this clock signal is really the only thing that is enabling this to change state or save a different state, right? So we don't see a negation here on the clock signal coming. So this is a positive edge D flip-flop. And 40 hertz, okay, great. That means, 40 times per second that we should be getting rising edges here to change this. Notice, though, that the clock signal propagating to the second flip-flop in our series is actually, all right, wired to the complement of the output, or not Q, or complement Q. What that means is that we're actually using the inverse of the save state, all right, to trigger the writing or the saving in the second flip-flop. And the reason that's important is we want to know that for this flip-flop to change, right, from 1 to 0 actually requires 2 rising edges, right? The first to write the first one, and then if it changes, the second rising edge to write the second. And the importance of that is that this output is going to be half as frequent as our clock signal every flip-flop. So our frequency going here is 40 hertz a second, or 40 times a second. That means the signal on this line is going to simulate a clock signal that's actually only 20 hertz, all right, or 20 times per second. And that halving is going to continue every flip-flop because it takes, 2 edges to actually change that behavior. All right, and the point is this signal will propagate through our design. So the more flip-flops we add, we're relying on the fact that this clock signal coming in, all right, is getting halved, all right, every jump between flip-flops, and that is actually what creates, our counting behavior. All right, so some other things to notice about this design is how we actually showing this count. So each individual flip-flop, all right, is saving a single bit of information, which is going to be a single unit in our binary number. So our first flip-flop here, we have Q out, and we notice that this is wired up to Q0. And again, it's important to note this is actually our least significant bit. The way we want to design this is so I can look at this value, and it's a left to right, read left to right as we normally would binary value, with our least significant bit over here on Q0. Again, the current state of our first flip-flop, and then we're going to add, for ours we'll have 4 bits here, and so we'll be seeing our however many bit binary number represented here. We're also going to add the 7-segment display, right, to double check that so we can see that easier. And then also for ours, because we want to count in a specific range, all right, we're going to add some reset control structure here to actually take advantage of these clears and presets. Notice in this design, all right, both preset and clear are wired up to the power, but we have this inverter on both edges. What that means is that these presets and clears are not they're not impacting this count at all unless we were to interrupt this power. Which again, in this design, there's no switch here, there's no interrupt possible, so those are basically locked out. And in this design, those will not be impacting the overall count. Right, this will simply count in 2 bits from 0 through 3 or 1 1, right? And then just keep going in cycles at 40 times per second. So this is a modification of lat design, right? Notice we've got 2 additional things here. We've got an extra bit, and so this is just showing you again how to propagate that clock signal through, right? Same thing. We're taking the complement of the output or the save state on the flip-flop before it in sequence. All right, and we're using that as a clock signal. Again, it's very important that this frequency is going to half, right? So this flip-flop will only change state, once for every 2 times this flip-flop changes state.